and we've developed a number of highly accurate and scalable time series classifiers. What's happened here? So the first of them was a tree-based system. First iteration of that was a system called proximity forest, and second was one called TS Chief. Can I suggest that people who aren't presenting mute their microphones? The second was a deep learning system, which is the current state of the art in deep learning for time series classification. Prima Paul, can I please suggest you mute your microphone? And then finally, we come to what I wish to present today, which is truly a revolution in time series classification. A system we call Rocket. The Rocket is the PhD work of Angus Dempster. 3 papers have been published now. The first one in 2020 on the initial system Rocket, 2021 paper on MiniRocket, and I'll also talk about some further development, the system we call MultiRocket. The underlying mechanism, or the key mechanism that Rocket relies on, is the convolution, a technique which has been popularized in deep learning. So you may be familiar with the idea of convolutions as applied in images. So on the left here, I show the result of applying an edge detection convolution to an image, and it highlights, so you get strong responses for parts of the images that are edges and weak responses for areas that are not edges. You can apply the same idea to time series. So here we have an underlying time series, and this is the result of applying a gradient convolution. So let me explain this in more detail. So here we have a convolution with 9 elements. So it is simply 6 negative ones followed by 3 twos. And to apply this, we simply multiply successive points in the series by the successive values of the convolution, so we can of the filter, so we convolve it. This results in this sequence of numbers. We take its sum, so the output of applying this filter at this location is the value 1.33. We can then run it along the series, and that results in a new series, which is the convolutional output. We use a very specific type of convolution, convolutions where the weights sum to 0. And this has a very specific consequence, that the convolution applies only to the local shape. It applies only to the differences between the values to which it's being applied. It doesn't, it is invariant to the offset. So if you were to add any constant value to the underlying series, you would get exactly the same output. An important mechanism for these convolutional filters is dilation. And this is simply the distance between the locations in the underlying series to which each successive element is applied. So here we see a convolutional filter. So the same convolutional filter as we saw before being applied with the dilation of 1. So each point in the filter is applied to the next point in the series. We can see that when we apply it to this series, we get an assessment of very local gradients. This is a form of gradient filter. If we increase the dilation to 2, we get slightly less local effects. As we move to greater and greater dilations, we move from local effects to more global effects. Now we're interested in doing classification, and we've started with an input series that we're wanting to classify, and we've applied a filter to it. We've got ourselves another series, whereas what we're wanting to do is to go from a series down to a single categorical value. So in some respect, we don't seem to have made any progress in reducing this large set of values into a single value. And the mechanism we use to do that is to extract a summary statistic from the convolutional output. We've developed a new one for our purpose of time series classification, which is the proportion of positive values. We simply look at what proportion of the values in the convolutional output are greater than 0. And it's that we pass on to the classifier, not the whole series. It is essential that this pooling operation, as they're known in deep learning, so this summary statistic, is coupled with a mechanism called bias. So bias is simply a constant offset which is applied to the series. So it has the effect of shifting the location of 0 up or down. So if we have a bias of 5, apply it to the same series, we get a much smaller number of positive values, much smaller proportion. If we have a bias of -5, we get a much larger proportion. And what the rocket systems do is simply exploit the power of these convolutional filters. So it turns out that convolutional filters can capture many different types of feature of a time series. So the same mechanism can capture frequency, amplitude, local patterns, and global patterns. So what the first iteration of our approach did was simply generate a large number of these convolutional filters. So 10,000 is the default that we settled on in the end. And then learn a simple linear classifier. So when the number of training examples is large, simply apply logistic regression. We found that ridge regression is a better form of linear classifier to apply when the number of examples is small, for 2 reasons. One, it's much faster because it can do much of the process in closed form, but also it has much stronger regularization, which is very important when the training data are small. So it means it can't overfit the data so easily. So Rocket, the first iteration, simply generated these filters randomly. So it selected a random length between length 7, 9, and 11. It then selected the 7, 9, or 11 weights in each filter, by random selection from a Gaussian distribution. It then selected the bias randomly using a uniform distribution between 1 and -1. It selected the dilation randomly in a uniform distribution between which resulted in dilations between 1. So dilations which are powers of 2 between 1 and the maximum, which is no longer than the series to which we want to apply it. There's a thing called padding, which essentially controls whether the resulting convolutional output is the same length as the original series or is shorter than it. And that's simply chosen at random whether to apply it or not. And then for Rocket, we use 2 summary statistics, so 2 pooling operators, proportion of positive values that I explained a second ago, and max, which is simply the maximum value in the output. And that's a very common pooling operator used in deep learning. So you can visualize Rocket like this. You have an input. We then have a large number of random kernels, each associated with a random bias. We convolve each of those kernels with the input, getting 10,000 by default outputs, convolutional outputs. And then we apply 2 pooling operators, resulting in 20,000 numeric values, which are then provided as the input to a linear classifier. So Rocket did indeed prove to be highly scalable. So what I'm showing here is on the right, the training time as you increase the training set size. So this is the same 1 million observations from the satellite data set. We present the times required to learn from this by Rocket with 100, 1,000 and 10,000 filters. And we can see that with 10,000 filters, it requires less than 2 hours. Whereas our previous system, which we were very proud about how scalable it is because it could learn this in less than 20 hours, as opposed to the 200 years that we estimated the then state-of-the-art would require. And the TS Chief system, which is a more accurate classifier than proximity forest, would require many weeks in order to do this. So we have a much more scalable system. TS Chief is of similar accuracy to the Hivecoat system, which was the previous state-of-the-art in accuracy. And you can see that Rocket, as we increase the training set size, green is Rocket with 10,000 features. Rocket dominates the accuracy at most training set sizes. So not only is it much faster than TS Chief, which was the then state-of-the-art in the scalable time series classification, it's also substantially more accurate. So scalability, it's important also to consider scalability with respect to time series length, because some approaches are quite fast with short series, but don't scale well to long series. Here we have a task where we've taken a series of increasing lengths. We can see that Rocket scales at a linear rate with respect to the series length, whereas Hivecoat, which was the most accurate classifier requires much more time. MiniRocket is our subsequent improvement on the rocket system. So we hit upon MiniRocket by considering the proposition that maybe the stochastic aspects of rocket weren't actually essential to its success. So MiniRocket is a variant of rocket that has predefined filters. They are predetermined. There is no stochastic element to their generation. So all the filters are of length 9. The weights are either -1 or 2. And we take all combinations of 9 values of -1 and 2 such that they sum to 0. So that means all combinations where you have 6 -1s and 3 2s. The bias in this system is actually sampled, so sorry, is one stochastic element. That's only for the sake of computational efficiency. We can sample in a non-random way, but it takes more time to do that. But the big difference is between, rather than sampling between the values of -1 and 1, we take the values as actual values from the convolutional output. So they are realistic values, because sometimes the range was much less than -1 to 1. So the values we get for bias are too large and push all of the outputs to close to 0 or close to 1. Sometimes they were too small, so the bias had very little impact. The dilation is fixed, so we simply have a fixed schedule which depends on the input length. Padding simply alternates between true and false, and pooling, we now only use the proportion of positive values. So we can visualize it as such. We have the input series. We now have a fixed predetermined set of kernels and biases. Because we know beforehand exactly what these are going to look at like, and because there are a lot of similarities between them, so they are only computed from 2 values, for example, we can highly optimize the process of convolving these with the input. We get, again, 10,000 convolutional outputs. And now we only apply PPV as a pooling operator, so we only have 10,000 numeric values which are fed into the linear classifier. This is much more scalable. So here's 3 examples of the most difficult. So the data sets from the University of California, Riverside benchmark time series classification tasks, which are widely used in the research community. These are the ones that take the rocket the longest time, and the decrease in time ranges from 66 times through to the speaker view is hiding the actual time on mosquito sound. But I think that the insect sound is the smallest one, and mosquito sound is the largest one. So we can see that there are orders of magnitude improvements in training time. And I won't show results for the comparison, but the accuracy is, if anything, very slightly better than the original rocket. And the main reason for that is because of the improved bias mechanism. I want to finally present the third variant system called MultiRocket. So here I'm showing the same architecture as Rocket. MultiRocket adds a transform onto the input series. So it takes the first derivative of the input series and also applies the convolutional filters to the transform series. And then it also adds multiple pooling operators. So if you think of each of these convolutional filters as capturing a different type of effect in the data, you can think of proportionate positive values as performing some sort of assessment of how often or how many of the locations in the series have that feature. We add the mean positive value, so that's how strong is the feature, how strong is the effect. The mean index of where the values are positive, so that is where does the effect occur. And then the longest stretch of positive values, which you can think of as an assessment of how dispersed is the effect, how strongly grouped together is it. We compare MultiRocket to MiniRocket in accuracy. So here we're taking the University of California, Riverside benchmark time series classification tasks. So all 115 roughly of them. And each point is one of the tasks. And we're plotting on the x-axis the accuracy of MultiRocket, on the y-axis the accuracy of MiniRocket. So where the point is below the line, MultiRocket is more accurate on that task, and where it's above the line, MiniRocket is more accurate. And it turns out that MiniRocket is more accurate 25 times and MultiRocket is more accurate 76 times. So it is most of the time more accurate. Here I'm presenting a comparison of MultiRocket to the current state of the art in this field of research. So the Hivecoat system, possibly partially in response to our work, has been substantially upgraded and has set new standards in accuracy. Let me, we have here TS Chief, which is our system, which was our first attempt at high scalability and which was equivalent or slightly more accurate than Hivecoat 1. MiniRocket, which I've explained, Inception Time, our deep learning approach, Arsenal, Dr. Sif, TDE and STC are components of the Hivecoat system. Arsenal is an ensemble of rockets, not mini rockets. And then Proximity Forest is our first attempt at scalable time series classification. What we have done here is applied all of these systems to the UCR archive of benchmark tasks. Then on each task, we've ranked them all on accuracy. So the lowest rank is the most accurate one. Then we've taken the average of their ranks across all the 100 and something tasks, and that's what is being presented here. So the average rank of Hivecoat 2 is slightly below 3. The average rank of MultiRocket is slightly below 4. the average rank of TS Chief is slightly below 5, and so on. These bars show clusters of these systems whose ranks cannot be distinguished statistically. So we cannot with any confidence say that the rank is actually a superior rank. So MultiRocket cannot be statistically distinguished from Hivecoat, but maybe that's just because there aren't enough tasks being considered. So MultiRocket I would assess as being slightly less accurate overall than Hivecoat, but not greatly so. In contrast, and I can't see the times here, Hivecoat takes a very long time. So I'm presenting here the total time to process the benchmark series. So Hivecoat requires 2 weeks to do that. TS Chief requires 6 weeks. Inception time requires 4 days on a GPU, which is a much more powerful form of processor. These other results are on CPUs. In contrast, MultiRocket can process the entire archive in just 17 minutes, and MiniRocket requires just 3 minutes. So if time is really critical, use MiniRocket. If accuracy is also important, use MultiRocket. If time doesn't matter and accuracy is the only thing which matters, then use Hivecoat. And all of the systems that are significantly less accurate than MultiRocket take more than a day. So there's just orders of magnitude difference in the amount of time required. So MultiRocket is both more accurate than them and orders of magnitude more efficient. Now, you should always be cautious when someone like me presents to you how fantastic the systems that they have developed are. So let me present to you here some assessments by independent groups. In fact, this is an assessment by the people who've developed the Hivecoat system. So they say Rocket is the best ranked and by far the fastest classifier and would be our recommendation as the default choice for multivariate time series classification problems. So multivariate is where there's more than one value at each point in the time series. Rocket wasn't designed for that, but it's trivial to extend it to it. And it turns out to perform extraordinarily well. And in different paper by the same people, so this is the paper where they present Hivecoat 2, they say there are currently 4 algorithms with reasonable claim to being state-of-the-art for time series classification. So they name Inception Time, which is our deep learning approach, TS Chief, our decision tree-based approach, and Rocket that I've just presented to you, and then their own Hivecoat. And they can, one of their concluding remarks is that Rocket is a very fast classifier that has state-of-the-art accuracy, and we believe it's the most important recent development in the field. So this paper was written before this group knew about MiniRocket, let alone MultiRocket. If you're interested in building upon this work, there are many things remaining to be done. There's plenty of potential for additional pooling operators beyond the 4 that we've identified as being useful. There's nothing magical about the kernels that we've developed. There's a lot of potential to find better kernels. Rocket we developed for classification, but it has clear potential for application in many other tasks such as forecasting, predicting numeric outputs, clustering, anomaly detection. You name an analytic task, there's potential to apply the Rocket features to do it. It's also likely that if you have sufficient data, it would be productive to use more powerful classifiers than simple linear classifiers that we've applied. And finally, these ideas may be applicable to other types of data beyond time series. So in conclusion, Rocket has revolutionized time series classification, provides state-of-the-art accuracy and many orders of magnitude less computation. MiniRocket achieves yet another order of magnitude speed up and shows that the randomness that's inherent to Rocket isn't actually important for its performance, for its accuracy. And MultiRocket provides a substantial gain in accuracy with modest computational costs. So thank you very, I should say that all three systems are out there. You can readily download them and use them. This is the work of an amazing team of researchers and the PhD work of Angus Dempster. So thank you very much for your attention, and over to you.
Thank you, Dr. Webb. Participants, if you have any questions or queries, please turn on your microphones and ask them, or you can post your queries on chat.
Maybe I should stop screen sharing so that we can see the chat more readily.
I have a query. I'm a researcher who's working on channel estimation, and I'm planning to use machine learning, so especially in wireless communications. How effective would be how this kernel would be effective in terms of estimating channel state information?
Sorry, I did not catch that. So I think the question was, how effective are these techniques at capturing some form of information, but I didn't catch what form of information.
So just it's like I'm looking for looking for a better kernel to apply in extracting channel state information for wireless communication. To get it more accurate, to develop a system that would help estimate these channel states more effectively. So,
I think that's exactly the form of application for which these techniques would be very useful. If it's not clear what the properties are of the signal that are relevant to determining the state, then these filters. So the evidence is that for many tasks, each of these filters, which isn't designed for that particular task, but for many tasks, each filter will pick up a very small amount of information with respect to the task of interest. And then the filters are uncorrelated with each other. So they're independent of each other. And so the linear classifier is able to very effectively put together all these very small amounts of evidence in order to reach a very concise conclusion.
Thank you, sir. Dr. Webb, I think there aren't queries yet posted by the participants. So without any further delay, I would like to propose a vote of thanks on behalf of our institute. On behalf of St. Joseph's College of Engineering and Technology, I would like to extend my sincere gratitude to Dr. Geoff Webb for sparing his time and efforts in spite of his busy schedule to speak to us. Today's talk on time series classification in terms of optimizations like in accuracy and training, it was quite insightful for researchers and artificial intelligence. And as a token of our gratitude and appreciation, we would like to present a virtual memento.
Thank you very much.
Thank you, Doctor. Thank you, Dr. Webb. And once again, thank you, Dr. Webb, for your efforts and for a very beautiful session. It was a great pleasure to have you with us today. And I would also like to thank my colleagues who have worked a lot to make this session a success.
Oh, thank you very much for giving me the opportunity, and I very much look forward to having some opportunity to actually meet you all in person sometime in hopefully the not too distant future. Thank you all very much.
Thank you so much, Dr. Webb. I'll probably email you right after the session. Shall we?
Wonderful. Thank you so much.
Thank you, Dr.
I'll leave you to it. Thank you. Bye.